What's up, kids? We're back on Mr. Murray's Mathland, taking a look at another calculus classic here. Uh, Finding relative extrema and intervals where a function is increasing or decreasing. The process is the same for all kinds of functions, and that would be you want to find the critical numbers of the function, and that's where the derivative is 0 or undefined. Those are critical numbers, right? And then we want to maybe test to the left and right using some kind of chart or sign chart or number line, something to organize that to basically see, if the derivative changes from positive to negative or vice versa. We call that the first derivative test. So again, and a critical number, remember, is a number where, these things are true. The derivative is 0 or undefined. But it also has to be in the domain of the function. So always worth considering what is the domain of this function that you're starting with, and this domain is all real numbers. If you were, if this was giving you pause for concern here, because that's really a radical, that's really the cube root of x squared, right? The bottom is the root. And so cube root is always defined. So x can be negative, whatever. And so that is all real numbers. So nothing to worry about any domain constraints here. So let's just get right into it. Let's find the first derivative, and it's already kind of set up in that power rule friendly format. So 2/3 times 6, that is 4x to the negative 1/3. Derivative of negative 4x is negative 4. The constant negative 5 drops out. And you may like to rewrite that as 4 over x to the 1/3, or 4 over the cube root of x if you prefer, minus 4. And now two things we're going to do. Do not forget about that there are two ways to be a critical number. Anywhere where the derivative is equal to 0, but also where is it undefined. And you see, because we ended up with this negative exponent that put this down here, that means that h prime is undefined at x equals 0. So that right now is a critical number we're going to have to investigate. Something's happening there. And now let's solve where is this derivative equal to 0. So this is an easy enough one. You might even be able to just solve it in your head. But if not, you could add 4 to both sides, take the reciprocal, cross multiply, whatever you want to kind of do to solve this here. 4 cube root of x equals 4. Divide by 4, you got the cube root of x is equal to 1. And then, of course, cube both sides. So x is 1. So you've got two critical numbers here to investigate. That would be 0 and 1. And so let's go. Let's make a number line. Let's be organized here. There's a variety of ways to kind of organize this data here. You're trying to do it in a way that's not too time consuming, but you don't leave anything out here. So remember, the idea is we're going to plug numbers into h prime. That's where we know the function is 0 or undefined at these two values alone, at 0 and 1. So everywhere else, h prime should be positive or negative. And we're using that to determine the behavior of h. So I like to label the bottom and the top. So let's just think about this. If I plug in anything that's negative, anything less than 0 into h prime, so that's into this equation here. So if you plug in negative 1, for example, into this, negative 1 into the bottom here will be negative 1. 4 divided by negative 1 minus 4. That's going to give you a big fat negative there. And that tells you that h is decreasing when the derivative is negative, or if you like to draw a little picture, this is all what's going to help you. So maybe do both. In between 0 and 1. Now that can sometimes be tough because you're trying to plug in non-integer values, like 1/2 or whatever, into this. But if you plug in, some positive value that's between 0 and 1, take the cube root of it, it's going to get even smaller. And when you divide 4 by that really small number, you're going to get something bigger than 4. So minus 4 is going to be positive. So that tells you in this interval h prime is positive, which tells you h is increasing. Right? It's got a positive slope, so h is increasing. And then after 1, when x is 2, 3, 4, whatever makes it easy for you to tell, put in 8 if you want the next perfect cube. Cube root is 2, 4 divided by 2 is 2, 2 minus 4 is negative. So the signs did change at each of those critical numbers, which tells you again that now h is decreasing. And it also tells you what you're dealing with at those critical numbers, that at 0, since the h prime change from negative to positive, or h is changing from increasing to decreasing, you've got yourself a relative minimum, or a local minimum if you prefer. And at x equals 1, it's the reverse, that h is changing from increasing to decreasing, so you've got yourself a relative max. So the direction said to find the coordinates of these relative extrema, so you got to plug back into the original function to get the corresponding y values. So h of 0, again trying to show our plugins whenever we do a plugin with nice notation. So h of 0 and that original function is going to be negative 5. And h of 1, plugging 1 back into h, will give you 6 minus 4 minus 5, convenient, nice numbers to work with. And you have 2 minus 5 is negative 3. Yep, I had to think about that for a second. That's it. So here we go. Now let's summarize our results. The coordinates, we have this is kind of an AP thing too, that this sign chart is for you to help you investigate and determine things, but it's never a final answer. It's never just the final justification. So it's there, it's part of your work, it's nice, but it's not the final. So don't expect the grader to extrapolate information from it. They make a constant point of saying that in their reports each year. So here's what we've got. We have a relative minimum at 0, negative 5. We have a relative max, and it is okay to abbreviate these kinds of things, at 1, negative 3. And intervals where it was increasing or decreasing. And this is also where, why it's important to consider the domain, because, are we going from negative infinity to infinity, or are there restrictions? So this function is decreasing from negative infinity up to 0, and I'm just looking at the, our chart that we looked at, from there to there, and from 1 to infinity. So negative infinity to 0, and from 1 to infinity, and our function is increasing between 0 and 1. And so there's all the information they asked for, kind of summarized. Hopefully it wasn't too rough, but I figured like a nice thing is to let's look at the graph just for confirmation, but also to examine and strengthen that understanding of what we just found with all that algebra. In particular, this critical number, which a lot of you, let's be honest, may have overlooked, that the derivative was undefined as 0. You may have forgotten about that piece. Ended up being a relative minimum. What does that look like on the graph? A place where the derivative is undefined, but was in the domain, and ended up being a relative minimum according to this. Now x equals 1 is a place where the derivative equaled 0, and it was a relative max. So that should be a nice, flat, smooth, horizontal tangent line. But let's take a look at the graph here. And here it is. I pulled it up on Desmos here. I mean, look at that. At 0, you can see that there's a cusp, but it is a cusp relative minimum, right? And, at 0, negative 5, just to confirm. And then it increases between 0 and 1, and you have that little relative maximum at 1, negative 3, and then it decreases again. And so that's going to happen when you mix in, cube roots or radical expressions with polynomials. You're going to get funky little combination shapes like this. So hopefully that confirmed the results, gives you a better sense of what it is you're finding. And as always, keep working hard. Let me know if you have any questions.